introduce our very own Yaser Sheikh, who's an associate professor here in the RI, and also right now the director of Facebook Reality Labs here in Pittsburgh. Yaser has a list of awards far too long for me to name here. His work has appeared everywhere from the New York Times to Wired Magazine, and focuses on connecting machine perception to understanding social behavior, human behavior. So this is based on a lot of not only incredible technology, but really understanding how that technology can inform how we communicate face-to-face in VR. I won't say more, I'll let him say it.
All right, thank you, Keenan. Can you guys hear me at the back? Yeah? All right, thank you all for coming. Obviously, the work that I'll be talking about today is work I've done with some extraordinary students here at CMU. It's been a privilege to work with them and collaborate with them. So I like to sort of start these talks with a question. Why do people move? And as far as I can tell, we can sort of separate these into two major reasons. One is to accomplish some form of physical goal. For instance, if I show you a video of this form, it's kind of easy to describe, right? If I asked one of you to describe what you just saw, you'd say something like a young man smashes a guitar in his backyard and then kicks it away. And if I asked somebody else, you'd come up with roughly the same words. And most of the work in computer vision, in analysis of human behavior, is of this form. This attempt to take videos and convert them into words or sentences, right? All the action recognition work tends to be of this form. How can we take pixels, convert them into words, sometimes in sentence structure? But there's a whole other reason why people move, right? And that's to communicate information. Even those of us with the best words sometimes need to have gestures to kind of complement what they're saying, right? And what's interesting is that because these gestures are there to communicate words and augment speech, it tends to be that these kind of movements are not well represented by speech itself, right? So if I were to ask you to describe what either one of these are doing in terms of words, we would struggle to do it. If I asked one person, they would describe it in a very different way and perhaps even struggle to articulate what it is. And so where language is an excellent representation for that category of movements, it doesn't appear to be a great representation for this half, right? So this kind of movement has, of course, been studied for many centuries by social psychologists and behavioral scientists, right? And they tend to take a taxonomic perspective on this kind of study. So, for instance, behavior is often separated into two categories: verbal and non-verbal, right? Verbal is stuff that's associated with speech. They care about phonetics, the sound of things, semantics, the meaning of things, syntax, and other things of that sort. And on the other side, in non-verbal, anything that is not speech-related, are things like kinesics, which is sometimes informally called body language, a terrible term. Proxemics, the kind of spatial distribution of individuals. Vocalics, haptics, how you touch one another, and so on and so forth. There's this kind of a distribution. And then further on, there are different sorts of taxonomies, different types of groupings that people describe. For kinesics, sometimes it's broken down into parts of the body. And then faces, for instance, well studied, are broken down in some famous work by Ekman et al. Into action units, different parts of the face and how they move. And those are then constructed into categories, constructs, like anger, fear, surprise, once again, words, right? And there's been really some pioneering work in recognizing these movements and behaviors from video as well. Hi, Marshall. Jeff Cohen, who's in the audience, has done some pioneering work in this area. However, this kind of approach in dealing with social behavior tends still to look at words as representations, like anger, like fear, the definition of these discrete categories. Let's look at one of these sequences that we looked at recently, right? So here's a social game called Mafia that we captured many years ago in the Panoptic Studio at CMU. And what you're seeing over here, I presume, how many of you are familiar with the game Mafia? So most of you, right? For those of you who are not, it's a social game in which some people in the group are secretly part of the mafia, and the other people have to try to figure out who in the group is part of the mafia or not. And there's no information. You just look at how your friends are behaving, and judging from how suspiciously or oddly they're behaving, you try to tell if they are part of the mafia or not. And so this is one such exchange. The man in the pink shirt accuses the woman in the green coat of being mafia, and she denies it. And then let's see what happens. All right, so she says, Jess, I think you're the mafia. Me? Why? So what's noteworthy here? The first thing that pops out to you is that two people independently pointed at her and said that she is lying, right? So there is something both of them actually saw. It's not so there's some measure of objectivity there. There was some signal there, right? And it turns out they were right. So let's look at it from another perspective and see if you can tell what it is. There's something there, right? But once again, if I ask you, describe it. What did you see? Can you give it in words, in a sentence? It's hard to say. This is another example I like to give. This is a protocol developed by collaborators at Georgia Tech. And it's an attempt to try to see if we can diagnose kids of being at risk of autism before the age of 2, before they're actually verbal, right? Before they can speak. And what happens is there's an examiner and the child, and the examiner gives the child a ball. The kid thinks it's a game, and so he gives it back to her. But she doesn't give it to him unless he asks for it in some way. So he nodded his head. She accepts this as a request. And then she holds it again, and he does something very subtle with his hands, if you look, which she accepts. The gesture he did was just to open his hands just slightly, right? And she accepted this to be, give me the ball, a request. Now, what word in English corresponds to this? Who taught the child that this means give it to me? There are people here from many, many different cultures, different age groups, backgrounds, yet we all understand what this gesture means, right? It's what the eminent anthropologist Edward Sapir referred to as an elaborate code that is written nowhere, known to no one, and understood by all. And so, looking at the video that I just showed, there are a couple of observations we can make about this sort of social communication, right? The first is that it's multimodal. Even though what I showed you was just a video and you were able to get it, we communicate through the sounds we make, the body movements we make, hand gestures, facial gestures. Our communication is inherently multimodal, right? The second is it's multi-scale. And this is a fairly confounding problem in that subtle movements often carry as much information or more information than gross and large movements. So for instance, my large movements of my hand might not carry as much information as a slight smirk on my face, right? So this multi-scale nature of the signal is a challenge in trying to extract signal from noise. Finally, it's continuous, right? It's not like I am putting a series of symbols at you. I'm doing continuous behavior, I'm moving continuously as I behave, and it's not a discrete set of categories necessarily. And then finally, it's coupled. I'm not making these movements in a vacuum. I expect that there's a receiver most often, that the receiver is responding to my gestures, I'm observing them and looking at it back. And so the model of communication that we pursue in the work that we do is that as a communication system, right? To look at this as scientists and engineers as a communication system where there is in fact a transmitter and the body is your social display device, right? That's what you're using to transmit information to a receiver. And you have a signal source receiver that looks at these signals and responds to them in some way and sends information back. So understands, interprets it, generates a response message, and sends it back and forth. And that in this interaction, there is an actual protocol that underlies this, right? This is really what all of the study of psychology and behavioral science has told us, that there is structure in this interaction, right? The challenge is measuring the signal, right? What we transmit with our faces, our bodies, and hands is exceedingly difficult to measure precisely. Yet that's where the information lies. And that's what makes describing this elaborate code and discovering the protocol underlying it so difficult. Sorry. This is not a new idea. This way of looking at interactions has been in literature for at least 20 or 30 years, right? People have looked at looked at social behavior in this way as a dynamical system of interacting or information exchange for a very long time. And in fact, Shannon even referred to this as an example of a communication system in his foundational work on information theory. So, very broadly, what I'll be describing is a very first step, an initial step towards a direction of work that we've been pursuing for a while, but it is only like the first or second step towards that. The thesis is that to discover this elaborate code, we need to come up with ways of predicting the future behavior of our partners. So when we're interacting with one another, a good code, its attribute is going to be that it'll be predictive of your future behavior. And the reason is because then it demonstrates that it contains information about the other person's behavior. And to start on this journey, there are three sort of major challenges. And this seems to suggest that these are equal-sized challenges, whereas I think this is probably the smallest one. This is slight. This one is a huge, open, unexplored area that will take probably several decades to unfold. And we've not even scratched the surface here. So I'll talk about these three modules of work. The first one is sensing, right? Now, why is it challenging to measure social signal? If you think about what we want to measure what the face is doing, what the hand and body are doing, and it is multimodal and it is multi-scale, and we have to capture subtle movements over an area which is fairly large, like almost 4 meters by 4 meters, and we have to capture subtle movement in a large area. This makes it very challenging. The second is that people, when they interact with one another, systematically occlude one another. So to talk to you, I will face you. And unless I put a camera right in the middle, which will of course interfere with the interaction, it's difficult to capture the interaction, right? And so in order to measure this, people have been building capture systems for many decades, right? So the first one was probably built here at CMU by Professor Takeo Kanade in '95. And since then, people have been building domes in Kyoto, in France, in Germany, in the UK, back in the US, in China, back in the US, also in the US, and then in Germany as well. And one of the things I find quite interesting is not only about the fact about how international this has become, but also the fact that each and every one of these groups is still working in this area. It's because, of course, it was a big pain in the ass to build these systems in the first place. So we better use them, but also it's just the truth. But also that the sort of scope or the space of research is quite wide and open. So I'll talk a bit about the system we built here, which some of you may have seen. It's in the basement on the B floor of this building, called the Panoptic Studio. So the Panoptic Studio has a bunch of projectors, HD cameras and VGA cameras. And if we step inside, you see the space is large enough to house a number of people interacting in this way. And the small dots that you see are VGA cameras. The large ones are HD cameras, right? And there are approximately 500 such cameras in this space, all of them synchronized. And what we can do with these cameras is something like this. Now, this clearly isn't a social interaction. So this clearly isn't a social interaction. But the reason why I show this is because it has a couple of attributes we care about. The first is that no smoothness, temporal smoothness or spatial regularization or any such thing was used in the production of this result. And second is, as an attribute of all of these falling systems, you can see there's a large amount of occlusion. And yet it's able to measure information in the presence of that occlusion. And so if we contrive it to make it as difficult as possible, people walking around a person, you can see what the necessity of these cameras are. The the blue pyramids denote the cameras that actually see the point, which is this one right here, as the people move, right? And so you see the people are reconstructed, and as they move, they sort of project these shadows on the blue set. But at any one point, we see about 40 cameras can view any of the occluded points. And because of that, despite occlusions, we can have persistent tracks of points that we're interested in. And so let's see what happens when we reconstruct this, right? See, the ball was reconstructed. His slight head movement requesting the ball is captured. And we're starting to get some measurements of those signals that we wanted to recover, right? That hand movement, that slight gesture, we now have some sort of a hook on it. This is that other sequence I showed. It's very interesting for me to see in these kind of cases how much the foot is correlated. When she started jumping, she induced him to start jumping, and then he induced him. And it's not a coincidence. There's a lot of this sort of almost like a dance that goes on, right? And really to foreshadow some things I'll say later, the ability to measure these give us an objective way to actually start studying them. So the key idea in constructing this was that we wanted to try to have this concept, which is used in machine learning sometimes, of boosting, that use many weak sensors to solve a hard sensing problem as opposed to a few so-called strong sensors. So a lot of low-resolution sensors allow us to have much more robustness to things like motion blur, saturation, occlusion, things that always plague sensing systems. But there's a challenge with systems like this, right? So it's good that we can measure the movement, but which point is that? Does that point have any meaning as we try to find structure across different people or across different subjects? And for that, of course, there's been a lot of work in the vision community in identifying anatomical landmarks. Most of the work has been directed at faces. And there are large data sets for faces, and there are many excellent systems, some developed here in Pittsburgh at CMU to detect these kind of anatomical landmarks. But the face is only one part of the signal system. There was a paper recently in Science that showed an example. This is not their example, but it's derived from their result. Asking sort of when you see this, do you feel Nadal has positive affect or negative affect? So who thinks he's feeling positive emotions right now? So approximately half. And I will presume the other half is either negative or don't know. How about now? So that removes the ambiguity, right? Who thinks this is positive? Oh, you guys are brave. Yeah. But you're right? And what's noteworthy is the expression is nearly identical in both cases, right? And what we use to unambiguously say it's positive or negative is not the face, but the rest of the body. And so it's important to have that. And this is what motivated myself and students in the group to start to see if we can get more robust measures of what points on the body are doing. This was the reason for doing it. And this resulted in a system that we built. This is a result of it, of finding key points across the body for multiple people. You can see this is actually how it runs in real time. And we released this as the open pose system that some of you may have seen or used. And in fact, I'm not sure why I'm showing this, because of course you must have seen this upstairs as well. I use this slide externally. One note I will say is that one of the reasons why we got here first is, I believe, because we actually didn't care about solving this problem. It wasn't that we wanted to solve the anatomical landmark detection problem. That wasn't the goal of the research. The goal of the research was to use it for something else. So we cared that it worked. And I think that that's actually key. Like oftentimes in research, we see people trying to solve problems for the sake of publishing the paper, as opposed to solving the problem. And I do encourage people to think about problem solving in that way. In any case, here is the result put to music. So we open sourced the system, and it's been used very widely for a surprising number of applications, from art to medicine to sports, and a number of other areas, automotive as well. And what that gives us for our problem is the ability to actually start to measure the movement of anatomical landmarks in these kind of interactions, right? So this is what the result looks like from a single view. And we can start to answer questions like, is it the movement of the hands that give it away? Is it the movement of the jaw? Is it the movement of the shoulder? And here, once again, the Panoptic Studio, the concept of many weak sensors working in unison to provide measurements, starts to have some strength. So even though the individual views might have errors, when we aggregate this geometrically across many, many views, the resulting estimates are very, very stable and precise, right? So you see these heat maps may not be very precise on their own, but when we run them through a robust match and triangulate them together, then we get a much better triangulation and estimate of where things are in 3D. So you see these are movements of multiple people. This doesn't use any priors about the shape of the person or the size of the person. So it works right out of the bat for the kid too. And once again, no priors were used in terms of smoothing or spatial structure. So even these sorts of odd or unusual movements are captured without any processing. So now we have the body. Prior work has given us the face. And it's important to ask, does that seem like we're starting to get more and more of the signal in a way in which we can study it? And what we found was that, in fact, the hand is a really important source of information that's surprisingly difficult to get. Even with markered motion capture methods, it's extremely challenging to capture because, once again, this is small, subtle movement, and it tends to occlude heavily very often. Makes it very challenging to capture hand movement. But when you add it, you see there's a whole sort of layer of signaling that you suddenly get between this stage and this one. And there's another layer of signaling that you get between this and this one as well. And while there are now body annotation data sets and face annotation data sets, what we found was there was not a single hand annotation data set out there, which was somewhat surprising. Nobody had made a large-scale data set with annotations of hands. And we quickly found out why not, right? It's because it's extremely difficult to do in a consistent way. So these are of course the same image. These are two different annotations that people did. Can you tell which is right and which is wrong? It's kind of difficult to tell, right? Even in cases, for instance, in the hand, if I were to ask you to annotate the knuckle, you'd do it fairly easily on this side. If you ask for it on the other side, most people would put it right over there. Whereas geometrically, the joint is in fact further down. That's where it actually is if you think about it, right? So getting this sort of consistency is extremely difficult, especially from different viewpoints. Imagine now you're not seeing most of the hand. And so once again, we went back to the capture system that we had. And we had this idea called multi-view bootstrapping, that if we have this many views, there must be some camera in which we can see a good view of the hand, where it'll be easier to detect what the finger and the hands are doing. And so that was the concept. We have multiple views. We run the detector on all views. It fails on most of them, but works on a few of them. We use the good views to triangulate robustly in 3D, and then project it to all the other views. And now we've automatically annotated images where it's difficult to annotate them. So in these two, it was easy. The system worked automatically. We used it to annotate all of those that were difficult. All right, so once again, in this case, you see the ones with the cyan boxes. The things seem to work well. We triangulated and reprojected, and now for free, we have an automatic annotation machine. And so we did this repeatedly. And we improved the detector, ran it again. It would work on more views. We would get more robust measures of hands in more and more challenging views, poses. We'd keep reprojecting until we'd get stability. And it stabilized quite quickly in just 3 iterations. So that's what it looked like originally, with just a small set of annotated examples. And then by the next time, it was more precise. And by about 3 iterations, it looked good. One surprising result was that which at least I found surprising, is that we just used 2 individuals' hands. In other words, it wasn't like we had a large set of diverse examples. We just used 2 individuals' hands to generate the data set. And it worked not just in the DOM on the data itself, but it worked on YouTube videos to a degree immediately, right? So this is a result from the data that we trained inside the DOM, working on a YouTube video once again in real time. And this is, of course, the demo that you see on the 4th floor, right? Hand tracking, face tracking was done in the same way. Now, if we go once again back to that same example, right? This is run on a single view. So this is not multi-view triangulated. This is how it's running on a single view. We're starting to get some of that measurement of what the kid's hands are doing in this case as well, right? What the kid's head is doing too. It's noisy, but we've started to get sort of like a feel on that signal. And once we start to triangulate in 3D, we get much better sort of stability of movement. And it turns out that kids are an excellent stress test of this sort of system. Oh, you haven't seen it yet, you'll see. This work was by Handball. This is Handball's son. The other kid was my kid. We experiment on our kids. It's terrible. It's terrible. All right, and then of course we can start to see interactions with objects as well, right? How do these sort of affect tracking? It seems robust to that too. We've released this data set. It's the Panoptic Studio data set, which includes 3D key points, 3D dynamic point clouds as well from the 10 Connects. But the story doesn't end here, even here, right? So if we think about this picture, one of my favorite paintings, there's a lot of feeling and depth in this painting. And if we were to take even key points and remove the background, we've lost everything. We have hands, we have the head, we have the positions, but the painting doesn't have all of that content that it had before. So we need to move beyond sparse key points too. And so the next step that we pursued was trying to get a full mesh of what the person is actually doing, to try to get that last level of detail if we can. And so there is a lot of work in this area. Prior groups have worked on body models. This is some groundbreaking work in 2005 on the SCAPE model by Angelov et al. And the one which is most popularly used by these days is by Matthew Loper, similar idea. The simple model, it's just the body. There are several data sets starting from the pioneering work of Blands and Vetter, but it's just the head. And there were no models of the hands that we could find, so we built one of our own. So we took these 3 models, Frankenstein them together, and fit them to a large number of poses that we captured of about 150 or 200 people inside the Panoptic Studio. And we used this to build one unified model of face, body, and hands together, right? With the goal of trying to track consistently. And this is a key point. There is important correlation in the way my hand moves to the way my face moves to the way my body moves. These are correlated movements, and to separate them out, track them, and then put them back together is worse than doing this all together. And in fact, even speech is correlated. And so we can track them. So you can see this hands being tracked here. Second. I'll get to it. Yeah, I'll get to it in a minute. The main reason for this is, first of all, we do no frame-by-frame tracking. The second is we're not using appearance information here at all. In other words, we don't have an average texture. I'll talk about a method in which we try to do this from a single view. We add that, and it stabilizes things a lot. Right? The attempt is we want to purposefully avoid any kind of regularization. There's a quote by Michael Black, which I like a lot. Regularization is the crutch of the weak. So we want to avoid. So this is an example. If you look at the classic methods of doing this, this is an interaction. You see, it's good to capture body movement, but this behavior of just moving your hands, it seems to lose a lot. No facial expressions, no hand gestures. But nonetheless, you still capture some level of signal. But if we add this extra layer of hand movement and body movement, there's a lot going on there. And then, of course, the graduate student ritual of IKEA furniture assembly. And one final example of subtle movements. Yesterday I was with my son's piano teacher, and I showed him this video without showing him the audio. And I asked him to look at the hands to tell whether this person was an expert, an amateur, and he said rank amateur. And I said, and asked him how he knew. And he said, pianists who actually know what they're doing have their wrists raised, their fingers are curved, and their particular movement is very different from this, right? So while I was depressed about my piano playing, what I was happy about was that the system was able to capture enough detail that an expert could look at just the movement and make that correct assessment about the player. All right. And so now we're looking at trying to take this outside the lab as well. This is work with Srinivas and Minvo on trying to see if we can capture it. Clearly you can see we haven't done the hands and feet and face yet, but it's an attempt to try to take this outside the lab. So this was sort of like the first two steps. Sensing, meaning can we get the raw signal about what people are doing? That was the construction of this dome. And then measuring, taking those signals and actually measuring what we can from those raw signals. Now in order to start to look at this, this is all preliminary work, it's unpublished work, but it's just, I'll discuss it to give you a sense of how we're thinking about it and where we're headed. So we designed a game, which we call the haggling game, which you saw actually a version of this just previously, where there are two people with something similar. Like someone has a heavy laptop, which is more powerful, another person has a lighter laptop, which is cheaper, and they have to sell it to a third person. And so we don't really care that much about the outcome of the game, but we wanted something which induces people to sort of debate and discuss and gesticulate as they talk. And so this is an example. There are two sellers and one buyer.
I was student. You want speed, don't you? Yes. For computers, yeah. So my computer is faster than theirs, but it's heavier a little bit.
It is heavier, so if you want to heavy, how much heavier is it? It's fine. I mean, mine's like has a medium weight to it, but mine has a very light weight. Bringing my weight medium speed. So wouldn't you rather have a lightweight laptop in your backpack with all of your heavy buttons?
The way it is in
Okay. So it goes on like this, right? So we captured this for 122 participants. There are about 180 of these games. And we're in the process of sifting through this data, but it allows us to revisit questions that scientists have looked on for many, many years and actually have the raw signal to start to examine and test them. This is an example of something that we just tried, saying if we think about the buyer's body orientation, right, like who they're facing, the thought we had while discussing was maybe it's the case that there's a bias, that the buyer would tend to face the person they're going to buy something from more than the other person in that group. And so we tested this because we could. That's 0 to 1, and when we looked at the orientation, it turned out that just a slight bias to the person that they were going to buy it from, right? And this was sort of easy to do. So that's halfway through if they were just looking straight on, but it tended to be that there's just a slight push towards the left. We were looking at things like proxemics as well a little bit, right? So to see there's this concept of having an intimate space, social space, a public space as bubbles around us. This is famous work by, I believe, Edward Hall. Hall? Yeah. And so what we found was the distance, he said, social distance was 1.2 meters, I believe, right? And we did find that to be, there's a range that he gave, the measurements fell inside that. But some of the interesting facts that we found were, and it's not a fact, it's early results, are that there is in fact a shape to the bubble. It's not a circle, right? The proxemic bubble is not a sphere around us. There's a very particular shape to how we face other people and where we like to place them in our field of view as it grows as well. It's a subtle thing which requires subtle measurement, and we can actually do that. So we'll be looking at some of those questions too. And there's a lot more to how people spatially distribute them than just their positions. So we're going to be looking at that as well. Anvil did some work in trying to predict speaking status on predicting whether an individual is speaking or not based on the other person's movement as well. So this is once again a classification task, largely to flush the pipeline in what we're doing. And so what he found was that if you look at the person's face, no surprise, you can tell when they're speaking or not, right? You can see the mouth flapping, you can tell they're speaking or not. If you look at the full body, you get something fairly comparable to it. And if you look at just the body, you can still tell when they're speaking. And that's because when people speak, they tend to gesticulate a lot with their hands, right? So there's still signal over there. Compared to just doing this fully randomly. And that's nearly a 50-50 chance if there are two people, of course. What's interesting is when you try to predict when the other person is speaking based on the other seller, the numbers are still surprisingly high based on when you can see what the person's face is doing, the other person's face is doing, what the face and body is doing, when the body is just doing, which tells us there's this sort of correlation between movements between people. And so these are sort of first investigations into this area. And some future work that we're working on right now is how do we capture subtlety in the wild? So one of the things about Marshall's question is because there's jitter, that means that the signal that we're trying to capture that's subtle is overwhelmed by noise often. So we need to improve that the precision of these measurements before they are actually going to be useful. So we need to improve that. And the second, of course, is how do we actually go from this sort of capture to a representation? How do we actually discover what this elaborate code is, what the grammar is, what the syntax is, what the morphology is, truly underlying this sort of communicative behavior? Now, a question I often get is, of course, this depends on culture, it depends on age, it depends on the times. And there is really one repository of information that actually captures the entire spectrum of that variation, and that's internet videos, right? People are continuously uploading what they're doing, who they're talking to, day after day, and it's this huge repository of social information. So if there was some way of extracting social signal from this data set, we would have the ability to start to study these questions at the scale that is needed to, in fact, discover something. And so really, like most of our work these days is focused on how do we measure signal from a monocular source. And this is work done by Dong Lai, who may or may not be in the audience. Yeah. So given this single input, that's the extracted movement. So this is a monocular view. A few caveats before I get too far in. Unlike OpenPose, which is a frame-by-frame method and which runs in real time, and which I would say I would have a high confidence would work on most videos that you provided, this one works in batch mode, right? And it requires you to have enough pixels on the person. In other words, you have to have a good high-resolution view of the person. So this is still a preliminary result. But of course, no talk on body gestures is complete without President Trump. Oh, sorry, this is not the full video. There's another president there too. So we have, all right. There are many interesting applications of, yes, Professor Bansal as well. Including animation, right? So currently to produce animations, you have to learn how to use complex software like Maya, learn the subtleties of animation, and you usually need teams to build rigs and other things of that sort. There's a growing trend to try to allow individual non-specialists to create animations themselves. So a promise of this could be that you stick a webcam and you can start to animate a character directly yourself and in real time. And so recently we released a Unity plugin for OpenPose. And the plan is to connect these pieces together to get this sort of monocular 3D mesh tracking connected to Unity as well, and allow people in live to connect a webcam and start to animate their behavior. Some of this work has informed what we do at the Facebook Reality Lab in Pittsburgh as well.
The hidden code itself, and it's not getting any features from the generated text.
So what you're seeing here, whoops, sorry. What you're seeing here are two people obviously wearing the headset, and based on measurements of what they're doing, we're able to animate photorealistic characters and let people communicate with one another despite distances, no matter where they are, right?
The hidden code itself, and it's not getting any features from the generated texture.
From the generated what?
The texture that's generated, I think.
Well, I mean, they both come from the same source.
I see.
They have the same latent variable that informs how they should generate these two components, but they don't share any components, at least in the V0 architecture there.
And so we've been making progress towards animating these more and more photorealistically. This is our latest result. Cool. That's a render. The application which fascinates me most in this space, and which is why at least I got into this work, is still, can we use some of these techniques to help with the diagnosis and treatment of behavioral conditions? Hopefully we'll get some time to revisit this problem too. And then finally, collaborative machines, right? Today, these kind of machines are tools that we use, right? They're not partners the way other people are. And I think part of the reason is because machines are blind to these sort of signals that we send one another, and that's what limits their usefulness as collaborators. With that, I will end the talk. Please do send me questions if you have any. I'm happy to take questions right now too. Thank you. Jeff. Thank you.
Could you say a little more about the monocular view and how that works?
Mm.
Where you're going with that?
So this is a submission right now to CVPR, but the core way in which it works is it builds upon what we did with OpenPose. So it's obviously using CNNs. And the idea is the minimum information that we need to figure out what the 3D position of an arm is the relative displacement between the body joints. And so we have neural networks only predict what the displacement is at each location. So in the image space, for every joint, it just tells the system which direction to look at in 3D. That's a minimum sort of thing that you need to estimate. And from that, you can figure out what the 3D locations are that connect different body parts. The way we get rid of stability issues is that we're using that same model of the mesh model that we had before. And across an entire sequence, we estimate an average texture, and we try to fit that to the image as well. And by doing that from frame to frame movement, there's a lot more detail that it can extract, and it sort of stabilizes the estimates over time. Right.
So if you're interested in the quality of the movement, motor control.
Yep. Yep.
Have that.
It's too noisy.
The precision.
It's too noisy. Yeah. So there is a paper that was published this year. I would encourage you guys to look at it. It's called Alpha Pose. They've Alpha Pose, and they've gotten good precision. I believe that we will get there in terms of precision, and this sort of adding motion in is critical to getting precision as well. However, in the end, there is so much you can extract from low resolution over compressed data, right? And so part of the solution, I think, also is over time we'll start to see better sensors on cameras, on phones, and from that perspective we'll get the precision that we need to. But I'm confident that we'll get there soon. And I agree with you that as it is, OpenPose is too noisy. The jitter that Marshall was talking about too, which essentially comes from there, is too much to get the sort of subtleties that we need from single views. Yes? With difficulty. So the way, there are two sort of two approaches. One, which fell out of favor very quickly, was to have a graduate student with a large calibration board walking around the entire space. What they came up with, what do they say? Necessity is the mother of invention, right? So they bought this large tent, white tent, and we have projectors in there. So the projector projects a checkerboard pattern on the tent, and then we use that to calibrate all the cameras. In another version we've built actually at the Facebook lab, we in fact have a large robotic arm which moves around the space and calibrates the entire thing.
How stable?
Say again?
How stable is the generation? Because you have some thermal effects.
It's actually, so thermal effects are an important one, but precision is actually really, really high. We've in fact,
Stability over time.
so stability over time, the best way to combat it actually, to be honest, was we installed a special thermal, like thermal regulation system in there, right? And
That's the physical equivalent of modularization.
No, it's not. That I call clever problem solving. That's what I call it. But one other source of error which we found, which was interesting, was we had to vibrationally isolate the structure from the floor as well. Because as you walk even, then that moves the cameras if you're going to get really precise about it. Yeah. Yes. Calibration is always fun. Yes.
So you have this beautiful quote about regularization. Although you know you're measuring multiple things still, right? So those should still obey the laws of physics. Do you consider that regularization to say, okay, I know that this arm is not experiencing infinite acceleration, right? I should be able to constrain.
Yeah, so seriously speaking, I think there are things like where we will never have any sensing, right? So for instance, if I were to say pressing fingers, those kind of things, where we can never jam a camera in between the fingers, you feel like you have to use some sort of physical simulation to do it. The challenge with much of that work is, I think if you want to make the case that physical simulation is the way to go, you have to scientifically validate that in some way. And to do that, you have to have measurements in some way, right? And so that's the chicken and egg problem. Where it's useful is where you don't have measurements. And then how do you build a simulation that you can trust if you don't have measurements to validate it? That's where I think it gets locked in. I agree with you that the laws of physics have to be away. I mean, that's not an argument we're going to have really. But the sort of ballistic effects which you usually have happen at very, very small scales and over very, very short amounts of time, right? What you're really trying to get is muscle activations. You want to get the viscosity of the fat and the tissues underneath. Those are things we don't have measurements for. And so it ends up that if you try to take a physical simulation-based approach, the number of unknowns explode. And it's just another regularization that you're adding there. With priors, they're not substantiated. So in practice, I haven't seen this help at all. It tends to not work well. Sorry? Clothing, yes, that's interesting. Yeah, so part of it is through annotation. So when we ask people to annotate things, they annotate what they hallucinate behind the cloth. But it's definitely a challenge. One approach which we're discussing on how to pursue it is to actually understand the relationship. There's some good work by Michael Black's group as well in capturing people both clothed and naked. And there are sort of approaches to try to reclothe people. Whereas I think the more important question is how do we actually measure the underlying behavior and movement that we want to get to.
No matter we're thinking on the other part of the work, like the molecular
Yeah.
You know, the way you were describing your learner
Mhm.
to request basically just this vector.
Right.
That seems to totally fair, depending on the context.
Well, I mean, the thing is, this all relies on annotation, right? So, for instance, as long as you know, I mean, this is a rough gauge, but if you look at it, you can reason on it despite clothing, oftentimes. So that's usually a good measure that with enough data, a machine should be able to do it too.
Good.
Yes.
So have you looked into like how verbal, so a lot of your examples like non-verbal stuff, have you possibly called it verbal and also social signal, for example, like have you seen like how it works?
So we've only just started, right? This is an example of, I'm not a big fan of this because it actually takes it and does speech recognition on the audio. I think what would be much more interesting is to take the raw audio and see if we can learn something to do with it. But yes, we have captured the audio. It's also available. We've not analyzed it. We haven't looked at it yet. It's all synchronized and it's, it's available for analysis, but we haven't looked at that problem seriously right now. It's one of those things where, there's a siloing of skills. Since we've approached this from a vision perspective, there's a whole other sets of heuristics and intuitions that come in with audio. We have to develop that. One group that's done outstanding work in this area is LP's group at LTI, Louis Philippe Morency's group. Yeah.
But there's also some work on biometrics from audio. like
Yes,
processing.
of course. Yep. Yes.
So I have a question more about on the psychological side. So for example, analyzing whether the kid has like autism disorder. So what kind of, I think the question is, it's not like what are we detecting in that side? It's like, it's not like how we detect something, it's like what kind of psychological construct are we detecting using computer techniques to kind of solve that problem? And you guys have like any ideas or like insights?
So the first is, I think we should be careful about diagnosing. What's much more likely as a useful tool is triaging. Like not saying whether a kid has autism or not, I think that's very far away, but rather classifying is the kid at risk of it or not. Should they actually see somebody? And the approach will be anomaly detection. Does the child respond in a way which departs from normative behavior, let's say, right? So you observe a lot of kids, you develop a model of normative behavior, and then because you can measure these signals, you can see how far it departs from normative behavior, flag them, and then have a specialist evaluate them. I think that's much more likely the way this would go, at least in the short term.
So going further down this dark road, I see a lot of these examples and I think, okay, Big Brother's watching me,
Yeah.
He knows what I'm going to do before I do based on my body language. If this technology falls into the wrong hands, what are some of the unintended consequences?
You mean like a big
What are you talking about? First of all, I have to thank you, Keenan, for saying if instead of when, really. So.
There's a privacy policy.
No, it's not. So I think it's a very valid question. It's a very it was one of the reasons why, while discussing this, we chose to open source it, right? So one was that we just publish it, but by open sourcing it, everyone gets access to it, everyone uses it. And I do think this is one of those cases where, because the technology is moving so quickly, legislators are going to have a challenge understanding it, seeing where it's going. We do have a responsibility, myself included, to in fact engage with civic leaders to make them aware of what's coming up and engage with it. But with all technology, it's this way, right? It is a two-edged sword. It's partly about what it is, but more importantly, how society chooses to use it. And this stuff can be used in a very sort of negative way. There's no question about it.
So along the same vein of nefarious, for face recognition and all kind of work for defeating like a certain type of
Right.
is there the same kind of thing?
I think this is too fragile right now, meaning that it is too easy a task to defeat these kind of methods right now. It's so premature. It's so premature. It'd be very, very easy to. But I expect, as you're suggesting, this will be an area in the future for sure.
Okay. More questions from us?
One last question about the data set of the Panoptic Studio. Does this data set contain like annotations for social interactions or something like that? Or is it just like a flat mark?
So almost purposefully, we've chosen not to do that. Okay, because the thought is, in fact, that this in fact frames the problem in a certain way, which I think is not the right way to frame the problem. I mean, this is my personal opinion. It's not the right way to do it. It may end up being that turns out to be the right way to do it. But I feel like, those gestures I talked about in the beginning, it's not a unique one. There are likely hundreds of thousands of such gestures, right? We want to actually discover and classify those, understand their relationships. And it's not going to come from like 4 categories or 6 categories of emotions. I think that kind of work, it appeals to the computer scientists in all of us. We like to discretize things, categorize things, and do it. But that's not really like, in my opinion, the real potential of the work here. Yeah. Other people may choose to do it, but that's not the direction we're taking.